So let me record first. Okay, kejap kelas saya terkeluar. Saya share balik. Bismillah. Ramai sangat. Alamak, tunggu je ke ni? Kejap. Sekejap kelas. Try to open. Okay. Okay. Okay, kelas. Okay, Assalamualaikum warahmatullahi wabarakatuh and a very good evening to all of you. Sorry. Okay, before I start, can you see the slide? Boleh nampak slide?
Tak nampak, Doktor.
Tak ada, Doktor.
Tak nampak pula. Tak nampak. Sekejap. Boleh nampak? Nampak tak?
Nampak lagi.
Kenapa lah Sampai macam ni lah. Tak nampak ni. Kejap ya. Aduh, hai. Stressful lah ni. Macam mana lagi? Nampak tak slide? Still tak nampak ya?
Tak nampak doktor.
Kejap. Okay, tak apa kejap sabar. Sabar sikit. Okay, bismillahirrahmanirrahim. Boleh nampak?
Nampak.
Janganlah macam tu. Jangan macam tu. Aduh. Okay. Okay, let's start class today. Okay. Aduh, sabar. Saya nak cari pen saya pula. Okay. Pen ni pun satu kena nak. Okay. Boleh ke? Itulah pen ni. Okay. Okay, so this week, basically we'll cover the last subtopic in the energy transport chapter. Okay, so which is we'll cover 3.6. 3.6 is about the equations of change for non-isothermal system, where the first one, the subtopic to the 3.6 is the energy equation. We go back to the energy equation, the fundamental, and then we go to the equations of mechanical energy, and the last one is the special forms of the energy equations, which is this is the additional topic for this chapter. Okay, so supposedly for this week we'll have 2 hour lecture and 1 hour tutorial, but because I have took the emergency leave, so I will combine the lecture and the tutorial for the class. Okay, so the textbook you can refer in page 333 to 336, and also page 81 to 82 in the textbooks. Can you hear my voice?
Yes.
Yes, doktor.
Boleh.
Boleh. So kalau saya terkeluar ke apa, you cakap sebab apa?
Kalau terkeluar.
Keluar, madam.
Aduhai. Boleh ke kelas nampak ke?
Slide dah tak nampak.
Slide pula. Aduh. Saya tak tahulah kenapa kat sini kecil kejap saya lost connection ni. Komputer ni dah okey sebenarnya. Laptop saya dah okey. Okay, kejap ya, tak apa, kita sabar. Actually for this week dia tak banyak sangat subtopik dia. Okay, nampak? Boleh nampak?
Boleh.
Boleh doktor.
Okay. Baik, kita cepat-cepat supaya kita tak ni lagi, okay? Okay, apa tadi lupa dah. Okay, so we will generalize the shell energy balance and obtain the equations of energy, a partial differential equation that describe the transfer of energy in a homogeneous fluid or solid. So basically, before we go to the equations of change, we need to generalize first the shell energy balance. Okay? Okay, so we go for the energy equations. So last lecture kita dah belajar the energy equation, right? Okay, so now we just so the equations of change for energy is obtained by applying the law of conservation of energy to small element of volume delta x, delta y, and delta z. Okay, basically it's a similar in energy balance and energy shell balance. Okay, so we consider a small cube, which is for the volume is del. For example, this is x, y, this is z. Okay, so delta x, delta y, delta z is the volume. So the law of conservation of energy is an extension of the first law of classical thermodynamics, which concern the difference in internal energy of two equilibrium states of a closed system because of the heat added to the system and the work done on the system. That is familiar as delta U is equal to Q plus W. So kat sini kita dah describe in the last previous lecture, right? So which is Q is the heat conduction due to the conduction, W is the work done on the system. Okay, here we are interested in a stationary volume element fixed in a space through which a fluid is flowing. Both kinetic energy and internal energy may be entering and leaving the system by convective transport. Okay, so kalau convective transport is due to the bulk flow. Okay, so that for example tadi kita ada small element, therefore kita akan ada the into the system, energy to the system, and energy out of the system. Okay, so heat may enter and leave the system by heat conduction. Kalau heat conduction is Q as well. So as we saw in chapter 9, the heat conduction is fundamentally a molecular process. Okay, so kalau Q heat conduction, we refer to the Fourier law, negative K dt over either dx, dy or dz. Okay. Work may be done on the moving fluid by the stress and these two in a molecular process. This term includes the work done by pressure force and by viscous force. So pressure force and by viscous force. So remember work done by the system kita ada apa? It's a pi V, right? So pi V is equal to P delta plus tau. So P here is due to the pressure force and this one is due to the viscous force. Okay, so in addition, work may be done on the system by virtue of the external force such as gravity. Okay, So this is the equations of first law of thermodynamics. So rate of increase of kinetic and internal energy equal to net rate of kinetic and internal energy addition by convective transport. This one is 1/2 rho V plus rho U. Okay, plus net rate of heat addition by molecular transport due to the conduction is a Q, plus rate of work done on system by molecular mechanism by stress, which is pi V. By stress system means that by the pressure and also the viscous stress. Okay, and then rate of work done on system by external force. Okay, so in developing the energy equations, we will use the the E vector, which include the first three brackets on the right side of the above equations. So it means that the 3 here is known as the E. Okay, kita panggil apa sih? Combined energy flux. Energy flux. This one you need to remember. Okay, compulsory to remember. Combined energy. Okay. So several comments needs to be made before proceeding. By kinetic energy, we mean that the energy associated with the observable motions of the fluid, which is this one lah, 1/2 rho V squared. Okay, V and V. So per unit volume. Here V is the fluid velocity vector. This one is refresh back. By internal energy, we mean the kinetic energy of the constituent molecule calculate in a frame moving with the velocity V plus the energy associated with the vibrations and rotational motions of the molecules and also the energy of interactions among all the molecules. This is assumed that the internal energy U for a flowing fluid is the same functions of temperature and density as that for a fluid at equilibrium. So this is U. This is kinetic energy. The potential energy does not appear in the equations since we prefer instead to consider the work done on system by gravity. At the end of this section, however, we show how to express the work in terms of the potential energy. So kalau kita lihat daripada last lecture kita cakap, this one kita akan consider in terms of kinetic and internal energy only, because the potential energy dia akan automatically appear. Okay. Okay. So now we try to do the shear energy balance. So the rate of increase of kinetic and internal energy within the volume element means that this term in the is the volume with times with the energy. Okay. Next, we have to know how much energy enter and leave across the face of the volume element. So delta X, delta Y, and delta Z. So kita ada, this is the area because of the unit. Ingat tak, unit kita times with the area. So times for energy, combined energy to the system and out of the system for X, axial, this one for the Y, and this one for the Z. Okay. So you need to times with the surface area. Okay, so in, out. So in and out, this one also in and out, this one in and also out. This one kat mana kelas? Yang kat sini lah. So dia 3 ni. Tadi yang the first one equal to E kan, so this E, so kita ada in minus E out lah. So kita ada for the X, Y and Z. Okay, the 3 axes. Keep in mind that the E vector includes the convective transport of kinetic and internal energy, the heat conduction and the work associated with the work process. Means that E is equal to 1/2 rho V plus Q plus IV. 3 term ni lah. Okay. Okay. So the rate of which work done on the fluid by the external force is the dot product of the fluid velocity V and the force acting on the fluid density times with the volume and the gravity. Or we can write like this one. Okay, density times the volume and the Vg for the X, Y, and Z. So we now insert these various contribution into the general equations. General equation kita yang kat sini lah. So masuk balik tadi. Okay, ambil E, sini E, and then this by the external force tadi. Okay, this is the external force. Okay, and then divide with the volume when delta X, delta Y, and delta Z are allowed to go to 0. So finally, we get this one, the final one. Okay, so this one we can rewrite as the del over dt 1 over 2. This one equal to divergence for the E combined kat sini means that you have for the X, Y, and Z, and also for the external force. So G here due to the GX, GY, and GZ. Okay. So this one in terms of the E lah, combined energy. Okay, so kalau kita refer baik tadi, this the three term here yang semua ni dia adalah E. Okay, so patah balik, this is the E. So you suka tak suka, you kena remember that E is equal to 1 over 2 rho squared or rho U plus Q plus IV. You need to remember. Okay. So this equation does not include nuclear, radioactive, electromagnetic or chemical forms of energy. Maksudnya dia tidak termasuk kepada energy productions. So that kalau guna the equations of energy ni, you need to plus the energy production. If your system have energy that produce, so you plus. If do not have, then tak perlulah. Okay. So the equation can be written in another form to include the potential energy per unit mass. Okay, from the external force tadi tu, it can be convert ataupun it can be written in potential energy unit. So which is finally kita akan dapat seperti inilah, just to show. Okay, so V here is the potential energy. Okay, so use vector identity in equations A4. This one adalah how to convert from this equation. Macam ni dia boleh macam ni. Sebab the density is the scalar and the V is also the scalar. So dia ada, kita panggil hukum dia. So from here kita kena boleh dia akan jadi seperti inilah. Okay. So finally, kita boleh includekan the term here, which this one into the equation. This one. So kita akan dapat in term of potential energy. Maksudnya term kita dalam bentuk ada potential energy, include the potential energy. So maksudnya kalau yang kat sini the equations of energy without the potential energy. So kalau kita nak involvekan potential energy, so that equation dia akan jadi seperti inilah. Okay. Okay, so kita sampai lagi purpose kita. Our target now macam mana kita nak produce kepada equations of change tadi. Okay, this is the basic lah dulu. Okay, now we go to the equations of mechanical energy. So equations of mechanical energy basically we no need to derive the equation. Kalau tadi kita derive daripada equations of energy tadi kan. So for mechanical energy we no need to derive. We will use these equations of mechanical energy and also the general equations energy to form special form of energy equations. So kalau lihat kat sini, the equations of mechanical energy, this is the equations, okay? Okay, so that involve the kinetic only. Kinetic, and this term, kalau lihat, is combined, and this is due to the rate of work done by external force. Okay, so kita combine. How kita nak combine ni? So the special forms of the energy equations, the most useful form of energy equations is one with the temperature appear. Sebab kalau kita lihat yang sebelum ni, either equations of energy or ataupun mechanical energy ni, they involve apa? Internal energy. Maksudnya kita lihat, kita ada internal energy and also the kinetic energy. So how to measure this one? It's very difficult to measure both of properties. Therefore, kita akan try to convert dalam bentuk temperature. Okay? Sebab kenapa kita nak kena convert kepada equations in term of temperature? Because temperature is easy to determine lah. Okay? And then after that baru kita boleh predict the temperature profile. Okay, so first we subtract the mechanical energy equations from the energy equations. This leads to the following equations of change for the internal energy. So how? Okay, equations of energy, maksudnya equations of change in term of internal energy. Dia adalah, dia kata dia tolak tadi kan. So energy, equations of energy minus equations of mechanical energy. So dia akan dapat this one. Cuba kita tolak. Okay, mana tadi? In term of this one, kita tolak kepada mechanical. This is mechanical. Okay, the first term dia ada 1 over ni. Yang kita ada ni. Balance dia apa? Tinggal yang ni je kan? Sekejap tukar warna. Okay. So kita akan tinggal inilah. Okay. So kita akan dapat ini nampak Okay. So what about the others? Di sini kita ada this one, ini. So kita tolaklah dengan yang ni minus this one. So kita akan dapat ni saja balance dia. Okay. Okay. So the equations of change can be written somewhat more compactly by using this substantial derivative. Kalau substantial derivative maksudnya du here over dt. This one saya tak akan details lah sebab sebelum ni kita ada. Okay. So kata tadi kita ada du sini kan. Bentuk del. So kita tukarkan kepada bentuk substantial derivative. So kat sini. So kita tahu internal energy in term of enthalpy dia akan jadi sama apa? Equal to H plus P over 2. So kita boleh gantikan du here with the H. So kita akan dapat seperti inilah. Okay. Sudah ada yang ni. Okay, so this equation number 1. So standard equilibrium, kenapa kita nak tukar kepada H? Sebab kita tahu H nanti dia can be related to the temperature. So standard equilibrium thermodynamic formula to evaluate the enthalpy in equations of combined energy flux. Tahu dH is equal to either constant pressure and constant temperature. So that dH is equal to this one. Okay. So kalau tengok kat sini dia dah ada over dt. Itu yang kita nak lah. So dt kita nak. Okay, so you boleh betul tu substitute lah. Okay. Okay. So tadi rho DH ni. So finally rho DH kita boleh simplifykan dia. So dia akan dapat seperti ini. Okay. Okay. So equating the right sides equation number 1 and equation number 2. Okay, this is equation number 2. This is equation number 1. So dia samakan. Okay. So rho DH yang kat sini tadi rho DH. So this term equal to this term. Okay. So finally you akan dapat seperti inilah. Maksudnya this kan, okay, you akan samakan mana tadi negatif mu negatif divergent Q negatif minus QV plus dP over. Okay. So ni sama yang ni. So you simplify, you akan dapat seperti inilah. So ni you bawa lah kat sini. So you akan dapat ni. Okay. So inilah equations of change kita. Okay. Equations of change. So you can refer to the appendix B8 in B9. Okay. Sekejap. Okay, so inilah equations of change tadi. You refer B8 atau B9 kat sini, nampak sini. Inilah dia. Okay, and this one. So kalau kita kat sini, dia dah berubah. Dia dah change ni kepada something. So how they change? Inilah. Sekejap. Okay, so when Fourier, the equations of change for temperature in terms of the heat flux vector Q and the viscous momentum flux tensor. So to use the equation, we need expression for this flux. Okay, so when Fourier law of equation 9 is used, the term divergent Q become plus divergent K divergent T. So this one become this. Okay, when Newton's law of equation 1.2-7 is used, the term tau here become this one. So the quantity given by explicitly in equation 3.3-3. Okay, so inilah kita punya target kita lah, equations of change for temperature. Okay, so we now discuss several special restricted versions of the equations of change for temperature. In all of this, we use Fourier law with constant K, and we omit the viscous dissipation term, since it is important only in flow of with enormous velocity gradients. Maksudnya, for term ini kita ignorekan. Sebab apa? For sistem kita sekarang enormous velocity gradients, maksudnya very large lah kan. And then constant K. Okay. So what will happen to this general equation? Apa akan terjadi pada general equations kat sini? Okay. So first, for an ideal gas. So kalau sistem ideal gas, so del ln P over del ln Tp is equal to -1. So this one dia jadi -1. So your equations akan become apa? Rho Cp dt is equal to ni plus 1. Plus dP over dt lah. Sebab tadi dia kata constant K kan. So bila constant K tadi, kita punya this one, dia akan jadi ni. Okay. So dia jadi seperti ini. And then this term for ideal gas, dia akan jadi -1. So balance, dia akan jadi dP over dt lah. So become this one. So for a fluid flowing in a constant pressure, for dalam sistem yang kalau constant pressure, so dP over dt equal to 0. So 0 dia akan jadi seperti ini je lah. Okay, And then for a fluid with a constant density, the density is constant. Below density is constant, then ln constant value it will be equal to 0. So finally dapat this one. Okay, and then for a stationary solid, V is a 0. For a stationary solid, kalau sistem ni dalam stationary solid, the V is a 0, therefore, okay, sebab you punya kat sini, the velocity kosong okay lah, so kosong. Okay, become this one. Okay, so if I'm not mistaken, this one ada masuk tau dalam final exam. I'm not sure last semester or 2 semester before that. So dia bagi you general equations. So the general equation ni, so kalau condition dia kata kalau ideal gas, so what will happen to this general equation? Dia jadi apa? So dia akan jadi ni lah. So this is the answer lah. Okay. Okay. So for this subtopic, the most important one is this one. The equations of change for temperature. So how kita nak guna equations of change for temperature in order to find the temperature profile. So previous lecture kita dah cari dah temperature profile by using shell balance kan, shell balance method. Okay, now we try by using the equations of change to get the temperature profile. Okay. Okay, now let's take a look. For the first, kita tengok contoh yang similar example. Okay. Okay. Apa ni? Table 11.4-1. It's a summary of the equations of for future reference. The equations given in both, okay, either nak tak kisahlah, derivative pun boleh. Often one may be content with the restricted solutions for making an order of magnitude analysis of problem or for investigating limiting cases prior to doing a complete numerical solution. This is done by making some standard assumption. Oh, either you nak yang tadi basic kita ini atau dalam bentuk derivative tu, so kita akan buat some of the apa tu kita panggil assumption, okay, so that dia tidak akan jadi terlalu complicated lah. So antara the assumption that we can make is assumptions of constant physical property. If it can be assumed that all physical property are constant, then the equation become considerably simple, and in some cases analytical solution can be found. Constant physical property, for example, the K is a constant, the density is constant, and the mu is constant, macam itulah. So assumptions of zero flux, setting tau and Q equal to 0 may useful for A here. Adiabatic flow process in system designed to minimize friction effect, such as venturimeter and turbine, and also for high speed flow around streamline objects. Okay, so kita boleh assume ini equal to 0. Okay, so now let's take a look for the first example, the previous punya contoh. Okay, sebelum ni kita dah buat this one menggunakan shell energy balance. Okay, now macam mana kita nak buat kalau guna equations of change? Sebab the objective is similar, to find the temperature profile. Okay, okay, first of all, kita kena tengok equations kita. Equations of change for temperature dia ada dua. Either you nak guna B8 ataupun B9. Kalau tengok dalam textbook, in the page 850 and also 849 and 850. Okay, you boleh tengok situ. Dia ada dua lah. B8 and B9. So apa beza dia? So kalau B8 ni, dia adalah equations of energy in term of Q. Okay, the second one, kalau satu lagi equations of energy in for pure Newtonian fluids with a constant density and K. Okay, and then if you want to use the B9 here, there is term kat sini tau. Okay. So this one atau kat sini kan? Sorry kat sini. So nampak V in term of potential energy kat situ. So you need to use the B7 also. B7 ni. Okay, nanti kita tunjuk macam mana. Okay, so here first. Okay, macam mana kita nak guna? Okay, pertama kita tengok equations of energy in term of Q, kita nak guna B8 ni. So kita kena analyse lah our system. Okay, so daripada tiga ni kita nak guna mana? Either the Cartesian coordinate ke, cylindrical coordinate ke, or spherical coordinate. Kita akan guna ni sistem kita, heat conduction ni, through the electrical heat source ni. So kita akan guna cylindrical coordinate lah. Okay, so yang lain kita boleh cancel out. Okay, and then kita analysis. Okay, our system yang kat sini tadi tu, is there any flow? No flow kan? So kita tak ada no moving fluid kan? So no flow. Therefore, we punya V is equal to 0. Right? Okay, V is 0. So you boleh cancel out the V is equal to 0 lah. So VR, kita kat sini. VR, so boleh cancel out. V delta, cancel out. VZ, you boleh cancel out. And then, ada lagi tak? Okay, and then you ada sini term V kat sini nampak eh. So you boleh cancel out. Okay, then number 3, you tengok dari segi apa? So the heat flux. So heat flux kita, the direction of heat flux in which direction? So heat flux kita dalam R direction kan? So heat flux in R direction. Therefore, kita ada QR kita is a function of R lah kan? Kita buat apa? D over DR lah. Ataupun kita buat selalu kita buat macam mana? R kan? So function of R. Okay, so kita tengok yang mana functions of R. So ni kita Q, functions of theta. So bukanlah functions of Z. Bukanlah. Okay, and then number 3. Nanti number 4. Apa lagi kita boleh buat? So our system is a steady state. So bila steady state means that the d over dt is equal to 0. Okay, so dia adalah kosong. Okay, and then apa lagi? And then kita punya density, the density is also constant, right? So bila density constant, so ln P ni, ln density ni kosong lah. 0 become 0. So finally yang tinggal apa? Apa yang tinggal? Kelas, kamu dengan saya ke?
Dengar.
Okay, boleh So finally kita dapat menaikkan ni je lah balance kita kat sini kan. Okay, so kita boleh tulis. So tengok the left side dah kosong kan. So you buatlah 0 is equal to negative mana tadi? 1 over R dr R Q R. Sama dengan seperti ini. Okay, and then ingat kalau energy equations dia hanya sampai external force, dia tak ada tambah heat of production. So sistem kita ada tak heat productions? Ada kan, daripada electrical heat source. Okay, which is SE kan. So, kita boleh tulis balik, saya tulis balik So tadi kita dapat 0 is equal to 1 negative R dr. So kita ada R QR tadi, and then kita kena pluskan dengan heat production atau energy productions, kita ada SE equal to 0. Right. Then you boleh rearrange. Kalau saya buat 1 over R, PR, so R, QR, sama dengan SE. Okay. And then buat R, QR dengan SE R. Kemudian kita differentiate lah. Sampai sini sudah kena seperti dia akan jadi similar to shell energy balance. Okay, kita nak selesaikan ni. Refer balik kita punya lecture, previous lecture. So sampai sini kita nak buat apa? Kita need to integrate the first and then you get the C1. Lepas tu macam mana nak solvekan C1 and C2 nanti? You kena buat apa? Masukkan dia punya boundary condition. Boleh ingat tak ni?
Boleh.
Ingat tak? Nanti kita dapat QR. Nak tak? QR is equal something plus C1. Maksud Q kita kena replace with the Fourier law. Negative K dt over dr. So baru kita selesaikan. Saya tak nak tunjuk sebab apa saya dah tunjuk yang sebelum ni. So you try balik rumah buat. Okay. So sebab saya punya target adalah kita nak mencari nak gunakan equations of change. Okay, now let's take a look for the second one. So kita ada yang apa ni? Okay, this one. So heat conduction with the viscous heat source. Okay, sekarang kita nak gunakan yang B9. So B9 for a pure Newtonian fluid. Kalau tadi yang first tu sebab kita tak ada fluid kat situ. So sekarang kita guna yang ni sebab sistem kita before this and yang ni sistem yang kat sini ni dia ada they involved with the Newtonian fluid. Okay, first kita nak pilih which one. Is it cylindrical ke, Cartesian ke, cylindrical ke ataupun spherical. Okay, you ingat tak yang previous kita buat yang ni, kita assume our dia punya curvature effect tu kita neglectkan dia. So it is like a plate kan. So kita kena guna Cartesian coordinate. Tu yang pertama. So you boleh cancel yang one. Cartesian. Okay, and then kita kena analisis lah. Number 2 kita tengok dari segi dia punya velocity. Okay, what about the velocity? Velocity kita sekarang dia adalah change to the dia ada ke tak ada sebelum that? Dia adalah sebab the flow system. So dia ada Vz change to the x kan. Okay, so kita ada Vz which is V as a function of x. So what about Vy and Vx is equal to 0. Right. So kita buat kat sini. Tengok sini. Ni ada Vx, Vy. Okay, Vx kita ada tak? Kosong. So Vy 0. Vz, ya betul kita ada Vz. And then okay, ni ada V. Okay, tak ada. Ni nanti last saya settlekan kat sini. Okay, so number 3. Sebab velocity kita tengok in term of temperature. T kita as a function of apa? In term of x lah. You said kita ada dt over dx. Okay, sebab dia change to the x, right? So kita tengok kat sini sekali. So dt over dz. Tak adalah, kita punya per x. So dtx, yes. Dty, no. Dt. Okay. And then number 4. Sistem kita apa? Kita adalah steady state. So bila steady state means that dt over d time adalah 0. Right. So kita boleh, ni is a 0. So finally, the balance yang tinggal apa? Kita akan tinggal, sekejap. Okay. So the balance kita akan yang ni saja, and also this one. So mu phi v. Okay, so the mu phi ni how to settle, kita pergi tengok B7. Okay, so sama. Nak tengok Cartesian ke, cylindrical ke, spherical. Definitely kita akan tengok Cartesian. So this one term kita cancel. Kita tengok kat sini. Nampak tak kelas? Ni macam sakit mata lah sikit. Okay. So kita tengok tadi. Berbalik pada kita punya tadi. Kita tengok VZ. VZ kita kosong kan? So kita cancel VY. VZ. VZ the X ni, this one DZ kosong. VY kosong. VX. VZ per Y kita per X kosong. VY kosong. VZ. VX kosong. VZ per DX. Kita punya DX lah. Okay. And then VX kosong. VY kosong. V ni per DZ. So kosong. So finally yang tinggal apa? Satu je. Kat sini. Okay, so this term kita masukkan dalam ni. Macamnya saya tulis balik tadi. So tadi, sekejap. So awak tengok sini dulu. So kita tinggal apa tadi ni? 0 is equal to K here plus ni kan. Okay, so kita tulis balik. So 0 is equal to K dt over dxp plus mu phi v. Right. Okay, and then 0 is equal to K mu. Okay, ingat. Saya tunjukkan kat sini. This one refer kepada B7. Appendix B7. So daripada B7 tadi kita dah simplify. Kita akan dapat apa tadi? dVz over dx 2. Okay. Okay. And then kita boleh simplifykan dia. Okay. So kita buat mu dVz over dx equal to 0. So you boleh integrate. Integrate lah. Integrate. So integrate you akan dapat negative K dt over dx minus mu d. You integrate ni dah kena Vz d v z over dx equal to 0 plus c1 kan? Tak ialah tak itu pun tak apa. Plus c1. Okay. Okay. So you boleh sampai sini you boleh continue lah. Okay. Macam mana nak settle ni? You guna boundary conditions. We need to continue to get the T profile. Sama seperti yang you buka balik kita punya previous lecture. So from here, you akan buat satu-satu nanti. Boleh? Okay. Sebarang soalan? Sebarang soalan? Boleh kelas? Isn't it?
Boleh.
Boleh Okay. So you kena untuk saya kalau my opinion for the equations of change for temperature ni is a very simple. As long as you boleh come up with the assumption ni tadi yang kita belajar ni. Dia punya maksudnya ni lah step dia. You tahu dia punya velocity, you tahu dia punya temperature change kepada apa, then you just cancel. Okay? Oh, saya terlupa. So kita tengok sini, kenapa tadi saya direct je ambil daripada yang sini. Saya tak tambah heat of production. generation. Sebab kita punya sistem tak ada heat of generation tau. So tak perlu tambah. Faham tak? Tadi sepatutnya kalau ikut basic tadi, macam ni kita kena tambah apa? Heat production. Tapi ingat tak, saya pernah cakap dengan you, kalau untuk viscose punya sistem, heat production dia akan automatic include DSV tu kan? Dia automatic include, so kita tak perlu tulis kat sini. Okay? Okay, so kalau tak ada question, I straight go to the tutorial. So tutorial, kita guna tutorial yang sama sebelum ni. Supaya kita can compare, we can compare both of it. Okay, group L. Group L kamu dah discuss kan tutorial yang week 10 punya? Dah kan? Yang heated sphere ni. Ada tak wakil group L? Lama, senyap je. Group L, ada tak? Kamu dah belajar tak? Okay, kalau senyap saya sudah belajar lah. Okay, so kita tutorial kat sini. Last lecture kita dah buat. Okay, so the first tutorial yang mana ni kita ada heated sphere. Ingat tak? Kita ada heated sphere. Radius kita R. And then dia place dalam large amount of stagnant fluid. So stagnant fluid kan? So kita nak lihat apa? Kita nak lihat macam mana kalau kita ambil shell, itu kita belajar kita ambil shell and shell balance dia and how dia distribute ataupun profile of the temperature to the surrounding dia, to the stagnant fluid ke situ. Ingat tak? So pada R is equal to radius capital R ni, the temperature is TR. For the R is infinity, the temperature is T infinity. Ingat tak kita buat macam tu? Remember? Okay, so sekarang kita nak buat menggunakan equations of change. Hari tu kita dah guna shell balance. So now we use the equations of change. Okay, you can use either B8 or B9. Terpulang. Boleh guna salah satu. Okay, so sekarang saya nak buat yang kat sini. B8 or B9. Saya buat kat sini adalah menggunakan kejap B. So saya menggunakan yang ni B9. Okay, you boleh cuba nanti kat rumah you try B8 nak macam mana. Okay, okay, sistem kita the first yang saya cakap dengan you bila kita nak buat kita kena tahu coordinate. So sistem kita apa? The coordinate is the spherical coordinate. So kalau spherical kita ada Cartesian, cylindrical, spherical. So kita choose the spherical. So yang dua atas ni cancel out. Okay. And then kita dah tadi tahu the fluid surrounding dia adalah stagnant. No moving fluid. Okay, no movement of the fluid. Therefore you ada VR, V theta and V VR, V theta and ni is a zero. Maksudnya VU memang kosong lah. Semua V adalah kosong. Okay. And then bila V kosong kita simplify. Tengok V yang ada. Okay, ni dia ada VR nampak ni. So kosong. V theta zero. Lagi kita ada apa ni? V ni. So zero. Okay. First one. Ni second lah second. Tadi the first kita pilih kita adalah spherical. Okay. Second step, tengok dia punya velocity. Yang ketiga, kita tengok apa? Dia punya, kat sini dia tengok dia punya DT. Kita adalah, sistem kita adalah, inilah, temperature kita is a function of apa? Temperature kita is a function of R lah kan? So T maksudnya dt over dr. Betul? So tengok dt over dr. Tadi dah cancel kan? So cancel. Okay, dt over dr, dt over d theta. So this one boleh cancel out. Dt of that can cancel out. Okay. And then kita tahu kita yang ketiga, yang keempat, kita adalah sistem kita adalah steady state. So kalau steady state, dt over d time is equal to 0. So this term kita boleh cancelkan dia. Okay. And then ni okay, tak ada, ni sama dengan yang ni lah. Transfer into the, okay. Sekarang kita ada tinggal dua je. This term and then this one. So kita nak lihat fee kita. So bila fee kat sini, dia adalah kalau logically sepatutnya kita tengok fee dia ni kan velocity, you kena refer B7. B7 tadi yang mana? Example. So B7 yang mana kelas? Yang ni. So yang ni. So kita kena ambil yang spherical. Sebab apa? Dia punya sistem spherical. Tetapi bila sistem, boleh je kalau nak buat satu-satu pun boleh, tak ada masalah. Tapi bila kita dah tahu sistem kita no fluid movement, so you dapat the new ni VN, so automatic kat sini you boleh ambil kosong. Dia tak ada movement kat situ. Ataupun kalau kita cuba, try kita buat so kalau tengok sini, you tengok V, kita tak value V kita semua kosong kan, so VR kosong. So nampak, automatic dia akan semua kosong. Okay. Okay. So finally yang tinggal yang ini sahaja. So you boleh tulislah. So untuk the left side sini dia adalah kosong kan. So 0 equal to K 1 over R squared D over dr R dt over dr. Okay. Then kita integratekan dia lah. Dah sama dah macam kita buat dulu. So you integratekan dia, you dapat C1. So bila dapat C1 kat sini, you integrate second time, you akan dapat this one. So you ada C1 and C2. So how to solve the constant integration here? We use the boundary condition. So boundary condition kita apa tadi kita tahu? Pada R is equal to capital R, T kita adalah TR. Pada R infinity, T is T infinity. So you can use one by one. Okay, so dibuat R is equal to infinity, R infinity something you divide with the very large value, it become 0. The T is T infinity. Therefore C2 is C infinity. Okay, then you masukkan C2. Then you buat second boundary condition when R is equal to capital R. So you masukkan capital R, T is equal to T infinity. Kat sini dia buat T, no, tak sure lah T infinity lah buat tadi. Salah betul lah, TR tadi kan dia buat. Patutnya TR. Soalan dia TR tadi. TR. Okay. So TR lah, bukan T0. Okay, so TR. Sediakan TR. Therefore C1 is equal to this one. Ni TR. Okay, so you masukkan C1 dalam equation. So finally dapat seperti ini. Okay. Boleh? Sebarang soalan tutorial ni you boleh cuba, okay, kat rumah nanti. Okay, let's say question number 2. Okay, this question number 2. So sama heated wire heated by electrical current, cuma dia dalam bentuk horizontal. Okay, so that you proofkan dia punya equation ni. So kita guna, hari tu kita buat shell, sekarang kita guna equations of change. Okay, so kita ambil yang B8. Okay, so use appendix B8 since boundary condition for the system in Q and T terms. Okay, so kita nak pilih apa? The first one kita ambil ke B8. So coordinate kita, Cartesian ke, cylindrical ke, spherical. Definitely is a cylindrical. Okay, sebab dia dalam bentuk cylinder. So di atas ni you boleh cancel lah. So you fokus kat sini. Okay, this one. So simplify. Ada tak move the movement of the fluid? The fluid is static kan? Tak ada kan? So VR, V theta and Vz is equal to 0. Okay, pergi tengok. So nampak ni VR kosong, V theta kosong, Vz 0. Okay. Lagi? Ada tak? Okay, melibatkan V kat sini. No velocity, therefore this term can be neglected. Velocity tak ada kan? So, kosong. And then, this is number 2. And then, our system is in a, kalau tadi saya nombor 3 saya buat apa? Q tadi kan? So, kita punya T, the T is in which, kalau kat sini T dia tak ada. So, dia R lah. Q. So, Q in the which direction? So, Q kita adalah dalam R direction kan? It's a function of R. Right? Okay. So, you buat kat sini. So, tengok Q. Dia akan maksudnya kat sini kita ada dq over dr. Okay. So, kita tengok sini ni dq over d theta kosong. dqz kosong. So, kita ada qr. Okay. Okay. And then yang keempat, normally baru cakap steady state condition. So, condition dt over d time is 0. So, here kosong. So, finally, okay. And then system kita the density is constant. Constant. The density constant. Ln constant dia akan jadi kosong. So, jadi kosong. So, finally yang tinggal mana? Satu sahaja. So, kita akan tengok yang this one. So, you buat 0 is equal to negative 1 over R dr R QR. So, ingat, ini adalah equations of energy. Tapi kita kena plus lagi. Ada heat produced tak dalam sistem kita? Adalah kan? Sebab heated wire kan? So, ditambah SE. So, ditambah SE equal to 0. Okay, so rearrange. Finally, you akan dapat seperti ini. Integrate. Okay, kalau tadi yang saya bagi contoh, saya kata you integrate sendiri kan? Ada jawapan juga kalau yang dalam sini. Okay, so you integrate dia, you akan dapat this one. Okay, so pada R is equal to 0, Q is not infinite, therefore C will become 0. Okay, so C1 0. So C1 0, so you akan dapat QR is equal to SER over 2 only. Okay, and then you substitute QR with the Fourier law. So QR is negative K dt over dr is equal to here. Then you lakukan second integration. Second integration, you get this equation. So you want to solve the constant integration C2. So in R is equal to capital R, the T is T node. Pada T surface dia kan? T node. Therefore you masukkanlah pada R is capital R, T is T node. So C2 dapat value. So substitute C2 into the equation, and finally you dapat this one. Okay, sini dah. Sebarang soalan? Any question, class? Class? Class?
Okay.
Okay,
Okay.
Okay, boleh faham?
Okay.
Okay. It's a very important for you to understand because definitely final exam akan keluar. Keluar tu maksud saya either shell ataupun equations of change, either one lah, tapi memang akan keluar lah. Kalau saya cakap keluar tu maksudnya sama ada chapter mass balance, bukan, momentum, energy and mass, dia akan keluar. Either you nak guna shell atau nak guna appendix. Dan kalau guna appendix pada I lebih mudah lah compare to guna shell. Sebab shell dia banyak step. Kalau appendix dia more to simplify. Okay, so try to score this one lah. Okay, equations of change ni. Okay, kalau tak ada soalan, kalau saya lihat in the modules, dia ada extra tutorial. Kalau you perasan lah. Okay, ni, this one. Contoh energy extra. Okay, this one dia tak ada solution dia. you need to do it first. Okay, so kalau you nak jawapan dia nanti, then I can share. Tapi buat dululah. Try to solve it first. Saya try buka. So kalau saya tak silap saya, kalau yang extra ni, the question is the recent question from the final assessment. So you boleh tengoklah pattern tu. Susah lah nak buka. Tak boleh juga. Okay, kalau tak boleh nanti you tengoklah dalam apa tu Moodles we check in the Moodles. Okay, so settle untuk chapter energy. Tak bolehlah kelas nak open. Dia boleh jadi. So saya tengok sikit lah sebab ada masa. Okay, this one I rasa final yang before this. Previous one. Okay, you boleh buat. Lemak tak hang pula. Okay, so you boleh buat kelas. Kalau tadi kita punya tutorial tu is a guided tutorial, dah ada jawapan kan. So you try buat yang ni. So kat sini it's a hollow sphere. So dia gunakan energy, equations of energy equations of change dalam appendix B8. So tengok 10 markah kat besar juga. So try buat, okay. So you kena proofkan seperti ini, okay. And then justify two assumptions that have been made to support your derivative. Maksudnya untuk you buat ni apa assumption you. So you state the assumption. And then define potential energy, kinetic energy and internal energy. Ini simple lah. Apa maksud potential energy? So kalau final exam ataupun quiz biasanya dia adalah yang soalan yang awal-awal ni. Macam bonus question jugalah. Okay, kejap. Ada satu lagi bawah ni. Balik kerap lah. Sekejap ni kelas. Sabar. Okay. So yang ni. Number 2, okay. Show the energy balance of a fluid element in space with dimension here, delta S, from the equations. So you kena buktikan lah macam mana they come out with this equation. Macam mana nak come out dengan soal seperti ini. So that you kena derive lah daripada satu yang tadi saya bagi step dia. So finally dia dapat seperti ini. Kalau you lihat tadi, dia sepatutnya betul lah. So enter Q. So yang dua term before akhir ni dia sebenarnya work done on the system kan, pi V. So pi V dia pecah kepada due to the pressure and viscous term. Okay. Soalan macam ini maksud you kena derive dia. And then number 3, responding pula. Check kelas. Soalan number 2 ni saya final ni, final assessment previous punya. Okay, sekejap. Tak nak. Okay. Bismillah. Tak nak. Okay, so the last one kat sini. So the equations of change for energy is obtained by applying the law of conservations element to small element of volume delta x, y, and z. Classify the term A, B, C, D, E for the following. Maksudnya you kena tahulah the term A ni apa. term B apa, C apa, D apa, E apa, F apa. Okay, so kalau tengok yang E ni apa? Change of the internal and kinetic in the system, kan? In the system. So kalau B ini due to the active energy. Number C due to the conduction. Number D because of the pressure. Number E due to the viscous, right? So kalau ikutkan yang D and E ni dia adalah combinations of pi V work done on the system due to the molecular. And then the F is the external force due to the external force. Okay. So the following number B, the following equations, the following is an equations of change for the temperature. Okay, betul. So based on the equation above, several assumptions have been made to derive the following equations. Explain the assumption. Okay, ni tadi macam saya cakap, ingat tak? So daripada general here, how it become this one? Kenapa dia boleh jadi seperti ini? Kenapa? What happened to the lone ni? Mana lone ni dah hilang? Mana term yang kat sini dah hilang? So you kena explain lah 4 markah ni. Kenapa lone kat sini hilang? Bukan hilang lah, maksudnya dia bukan value kosong kan? Dia is due to -1 kot. So -1 jadi positif. So DP kan? So negatif tadi kata saya dia adalah gas flow kan? Ideal gas flow, yes, very good. Ideal gas flow. Okay, so Q tadi kenapa jadi ni? Sebab the K is a constant tadi kan? So you boleh tukar. And then this one kenapa dia 0? Dia ada tadi. You tengoklah tadi dalam lecture note saya. Okay. Okay, so bentuk dia macam ni. Untuk soalan kalau quiz pun saya rasa dia akan simple macam ni. Ataupun final pun mungkin akan beginilah juga. In fact, I rasa ni final ni. Kalau yang tak silap saya nombor 3 ni. Soalan 3 ni semua final ni. Okay. So try to do it first. Okay. This one you kena derive lah. Okay. Sebarang soalan before kita dismiss.
Ada, Doktor.
Tak ada. So, sekejap saya nak ni. Okay. So, kalau tak ada, untuk group L, dalam WhatsApp group you dah ada dia punya, apa tu? Apa tadi tu? Attendance link. So, you fill in the attendance as a proven lah yang I dah buat kelas. For group saya nanti saya masuk saya tak sempat lagi. And then I'm sorry sebab saya ambil waktu weekend kamu untuk buat kelas, okay? Sebab kalau saya tak buat this weekend, so kita dah masuk satu lagi minggu depan tu, dah jam sikit lah, dah masa tu agak padat dan dah masa yang sama you nak ada quiz. By the way, you have quiz next week, okay? Next week you akan ada quiz, cuma I'm not sure either dia nak buat hari Jumaat ataupun hari yang manalah kan. Sebab sekarang dia menunggu saya lah. Okay, at least saya dah habis kelas. So depends lah pada coordinator which is Puan Nadia. Dia nak buat hari apa. So nanti saya akan update ataupun you boleh tengok daripada models lah. Okay. So kalau quiz dia adalah multiple answer. Maksudnya ABC. Dan juga dia ada simple answer. Simple answer tu pun macam you kena tulis dan you kena scan lah juga. Tapi it's a simple question. Okay, and then you kena attach juga. Okay, itu sahaja kelas untuk hari ini. So thank you so much. See you insyaAllah next week. Okay, Assalamualaikum.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.